Okay, so in an attempt to make a contribution to this class, I have modeled a number of the basic types of orbits that we'll find our satellites in. And the ones I have here are geostationary, polar, Molniya orbits, inclined orbits, specifically like low Earth orbit, and geosynchronous orbit. Now, geosynchronous and geostationary are actually two different kinds of orbit. It'd be more specific to say geostationary is a subtype, a very special type of geosynchronous. So we'll start with the geosynchronous satellite and just kind of see like from the set time. So we'll fast forward time. So generally, a geosynchronous satellite will maintain its general position over the ground all day. It will have some movement up or down, as we're kind of seeing here, but especially as we're coming out to the light side, you can see we're looking at pretty much the same spot throughout the rotation. And so what this means is we have an orbital period of 1 day. It takes 1 day to complete a circuit around the planet, right? So that's great. The orbital periods make a big difference because it also determines the speed of the craft, right? So if you'll notice, this is 1/10 scale, but it's a little over 1,000 meters per second. So now if I go to the tracking station, type of geosynchronous inclination, and geostationary is always equatorial. So this has a problem because it has a limited range, right? But geosynchronous presents the same kind of problem because, as it moves up and down ever so slightly throughout the day, maybe it loses connectivity to some latitudes. But it stays perfectly still the entire day, maintaining the same speed. So if I can actually go to surface speed right here, so I change the surface speed, I'm tracking, it's 0. It doesn't move, so it's perfectly stationary. So I'll hit up another one now. So like or the actual speed of the craft. So we'll go to polar. So a polar orbit is unique because it's the only type of orbit. So it's very, very unique type of orbit, and so it's kind of important to be aware of that. It might be a bit too fast. So as the planet moves around in its orbit around the star, because of the unique way that this orbits, it will eventually again see 100% of the planet. This is very useful for mapping. So geostationary is good for communications, geostationary is good for mapping as well, but only to a limited point. Polar is the best mapping orbit. And I have the green lines here represent connectivity from various satellites to other satellites that I have modeled here. So you can kind of see, that one's going up that way. Here's this one going this way. I have them going in various prograde and retrograde. So prograde means that it's turning and orbiting with the rotation of the planet, and retrograde means it's going the opposite. There's only one country that really launches retrograde, and that's Israel, because they don't want to drop debris over their neighbors. That kind of makes sense. Okay, so let's go to an inclined orbit. So an inclined orbit, this is just what it sounds like. It's just an various inclinations, because it doesn't really matter. And so they likewise will see a very wide area of the planet as they go around. It doesn't have to be a circular orbit. It could be an elliptical orbit. For a lot of different purposes, it doesn't really matter, what the orbit is, depending on what you're launching, what your satellite's job is. But most satellites find themselves in some sort of pseudo-elliptical inclined orbit, just because it's cheap to launch. So back to the tracking station, and then Russia came up with that so they could monitor both us and them. So I have two here, two Molniya satellites. I have a northern one that monitors the northern hemisphere and one that monitors the southern hemisphere. Now Molniya orbits are special in that they're at around 63 degrees inclination, and they have a orbital period of 1/2 of a day. They are slightly different from a tundra orbit. A tundra orbit shares the same inclination. However, the tundra orbit has a orbital period of 1 sidereal day. So anyway, so these are interesting. The apoapsis, apogee, it just kind of depends on who you're talking to. But they'll spend an inordinate amount of time like hovering about. So it looks like they go real fast around the bottom, but then they come up here and they hang out a lot at the top side, and generally over the same area too, which is nice. But then they zip around the bottom. So I'll kind of like zoom out so we can see just how much acceleration there is. So like this particular one going from at the apoapsis, it's coming up to about 500 meters per second, and then as it comes down, it's gonna get close to about, just about 3,000, almost 3,000. So it accelerates pretty significantly. So you have to keep in mind, or the closer it is, again, the faster they go. So I'll take a look at the southern one, since that's more in the sunlight board, but I don't want to. So this is going to come around up here, and then it comes down and has a long time. They spend about 2/3 of their orbit focused on the specific area that they need to be at. So now in synchronous, you can get 100% coverage of the planet, generally speaking. You might combine that with some inclined orbits too, some geosynchronous. And again, there's also, you have geostationary, which is at the equatorial plane. Geosynchronous can be at any inclination or any plane. Let me fast forward this and watch them do things. They can be at any plane, but they still have an orbital period of 1 sidereal day. So you can kind of observe this as they're staying put in relation to each other. All of my geostationary and my geosynchronous satellites are all staying put, with the exception of angular velocity. So then the Molniya orbits, of course, again, they get going pretty quick as they go around the bottom. And the closer you are, the faster they go. So the polar orbits, looks like my polar one's got a little out of whack. That's alright. But hopefully, like, seeing them, especially modeled at, a speed that we can more easily comprehend, and just seeing them in action has helped, like, everyone visualize how this works. So, hopefully I helped. If you have questions, how they're launched into those specific orbits, why we launched them into those orbits, I can. But a big deal is they got, again, like, a satellite at, like, geostationary has a harder time getting up to the northern regions without the help of a polar relay or without using a Molniya. So most satellites are launched in constellations of 3, because 3 creates a nice triangular pattern there. I could delete them, but I don't want to. I spent too much time putting it together. So I could show just fewer lines. So like direct connection. So this is oh no, it does not have a direct connection. So it's using a relay. So I'll show the second step. So right here we're watching how the relays are interacting to reach the one point where we, like, I have a receiver on the ground. So it hits each of these polar, and it uses the high incline. So polar one, yeah, use the high incline and then gets there. And we can pick it's geostationary. So it's also using the polar one to help out, to pick somebody a little bit further away. Geosynchronous. So it's using the same route. So in the same way that you have networking, the satellites will network with themselves as well. It's kind of important to keep that in mind. While you're always going to try and maintain connection probably to one particular satellite, you can't, unless it's geostationary or geosynchronous, in which case you can, but more than likely to communicate. Back home you're going to be communicating through a relay, a network of satellites working together. Again, hopefully the visualization helped. If you have any questions, feel free to just stop me and ask. Thanks.